Hello and welcome to On the Spot STEM. Today we're going to be tackling a math problem that's actually very simple in nature. It only uses at maximum multiplication and addition, but it requires very sophisticated thought and a lot of motivated moves, and is a very good way to show how math isn't about the actual computation, but it's about the reasoning that goes into it. Well, without further ado, let's begin. So, the problem statement. So, if you don't like this problem statement, I also have it written in English. You got a bunch of positive integers adding up to 20. What's the maximum product? And I think a lot of people would prefer this as opposed to the previous way. Well, let's keep going. Let's look at some examples of what we can do. So, 10, 8, and 2. That's an example of a bunch of positive integers that add up to 20. What is their product? Well, 10 times 8 times 2 is equal to 160. And for the problem statement, we want to maximize that number. We want to pick the numbers such that the product, in this case 160, is as big as possible. Well, let's continue looking at another example. For example, 5, 5, 5. These numbers add up to 20, and their product constitutes 625. Obviously, 625 is greater than 160, so we would prefer 555 as opposed to 1082. And 1082 is definitely not the maximum way. However, is 555 the maximum way? I want you guys to take some time for yourself. What's the highest number that you can get? And I would suggest that you pause the video right around here to experiment by yourself with some scratch paper, I don't know. If you would like to see the solution, continue watching. Well, the answer is 1,458. One solution to get 1,458 is 2 plus 3 plus 3 plus 3 plus 3 plus 3 plus 3, which is equal to 20. And 2 and 6 threes multiply out to 1,458. How do we know that 1,458 is the best answer that we can get? We actually have no guarantee. The only reason you know that it's the highest number is because I told you so. So, what we're actually going to be doing in today's video is proving that 1,458 is the highest number. And this is a very important thing to note, that mathematics isn't really about the final answer. It's the proof that you take to get to that final answer, and that's the more important part, the process of getting to that answer. And that's why we're going to continue looking at that for today's video. Well, here's some quick observations that we can make. If we had a bunch of positive integers adding up to 20, we only have so many options for what those positive integers are. It could either be 1, 2, 3, 4, 5, all the way up to 19 and 20. Well, we should never need to use the number 1. This is evident because using the number 1 does not increase the product, but it does take away from the sum. We would rather have one of our other numbers be bigger rather than use 1 because it never helps us increase our product. And since the goal is to get the maximum product, 1 is kind of useless. Here are some other numbers that we're just going to play around with. For example, let's look at the number 4. Is there ever a time where we need to use the number 4? Well, if you look, you're going to notice that 4 can also be, instead of using 4, you can also use 2, 2. And you can use that because it has the same sum as 4. It has the same sum as 4. And since 2 times 2 equals 4, then we really don't have a reason to use 4. We could always just use 2 and 2 instead of 4. Let's look at some other numbers. For example, 5 can be written as 2 and 3 as opposed to 5. And since 2 times 3 is equal to 6, that's already beating 5. We actually should never use 5 because why use 5? Because if you're using 5, you might as well use 2 and 3, which is going to be bigger, which is going to lead to a bigger product. We can continue doing this method for 6. 6 can be broken down as 2 and 4, and 2 times 4 equals 8, which is much better than 6. And for example, even big numbers like 17 can be broken as 2 and 15. And 2 times 15 equals 30. That's nearly double 17. In general, if we have x, instead of using x, we could use 2 comma x minus 2 and that's going to be greater than or equal to x for x greater than 3. So what you're going to be seeing is that for any x greater than 3, for example 4, 5, 6, 7, 8, 9, 10, all the way up to 20, we never have a need to use them because they can always be written more efficiently using 2 and x minus 2. Well, what can we conclude using that knowledge? We now know that we never have to use we never have to use any of those numbers, and the only numbers that we need to use are 2s and 3s. Those are the only useful numbers. Let's continue going. Now we need to decide when do we want to use 2s or 3s, because there's lots of different ways to use 2s or 3s to make a sum of 20. One important thing that we can do is, we first note that 2 plus 2 plus 2 equals 3 plus 3, which means that if I use 3 2s and 2 3s, it's going to take away the same amount of juice from our total sum of 20. However, what gives us the higher product? Note that 3 times 3 is greater than 2 times 2 times 2. Since 9 is greater than 8, there really is never a case where we have to use more than 3 2s. Because if we had 3 2s, why not just replace it by 2 3s? It'll take up the same sum, but it'll give us a greater product. So, using this knowledge, we know that we never actually have to use 3 2s, and we should never have more than 3 2s. Well, if we can't have more than 3 2s, then we can either have 0 2s, we can have 1 2, or we could have 2 2s. And because we need our total sum to be 20, we are forced to use 1 2. Because if we use 0 2s, then the sum we have left is 20, and you can't make that with only 3s. And if we use 2 2s, then the total sum left is 16, and we can't make that using only 3s. We can only make 18, which is the value given if you use 1 2. Therefore, we have to use 1 2, and with the remaining 18, we use 6 3s. And that gives us our final answer of 1458. This means that we have actually proven that 1458 is the greatest that you can get. So, let's look at our final proof as an overview to make sure we're doing something right. Well, we established that we never need to use 1s because they don't help the product. We also established that we never need to use numbers such as x greater than 3 because x can always be broken down into 2 or x minus 2 and x minus 2, which will be better than just using x. We also noticed that using 3 or more 2s is inefficient because we might as well use 2 3s instead of 3 2s. And to make sure that the total sum can be made by 2s and 3s, we have to use only 1 2 and 6 3s. And we get our final answer, 1458. So now we have proven that 1458 is the very best answer, and it is a very satisfying feeling because no matter what anybody else tells us, we know that we have the highest answer that we could possibly have. So, here are some cool follow-up problems based on this because this problem has a lot of different ways in which you can expand this. First of all, can you write a solution for any number, not just 20? Based on what we learned about the nature of using 2s or 3s, does the number 20 actually matter? And can you write a general solution for any number like 100 or 552 or 7,958,493? Another question is, why was the most efficient number 3? In the end, the problem ended up being how efficiently can I just pack 3s and use 2s as the leftovers. An important hint is 3 is the closest integer to the transcendental number e. And this is a really cool way to observe. And if you know some calculus, this might be a really interesting place to explore, and because e shows up in a number of contexts. Our final question is, what is the answers when the numbers don't have to be integers? For example, what if I could just use 2.5, 2.5, 2.5, 2.5 all the way up? Or what if I just packed in a bunch of e's? Who knows? This is a really cool problem to explore and will probably involve some calculus of sorts. Also, I wanted to talk about the takeaways from this problem because this problem is a really good way to understand how math logic puzzles work. Some quick takeaways is, for future problems, you should try random examples. When you have no idea how to approach a problem, the best way to take care of it is to try smaller cases, maybe draw a diagram, basically get stuff out of your brain and onto paper. Another thing is that math isn't about big computation. A big misconception people have is that as you reach higher levels of math, it's just multiplying bigger numbers, working with bigger numbers, and doing mental math or some sort. Math isn't about the computation. It's about the logic that goes into a solution. It's about how genius how genius a solution you can make. Finally, finding the answer is only one aspect of the problem. The proof is much more important because we have no way to know if our answer is correct or not. But if we have a proof, we have with 100% certainty our answer is correct. Thanks for paying attention and hope you like, subscribe, and please comment your solutions to our follow-up problems or comment any other interesting problems that you might think go along with this theme of math. Thank you.